All right, boys and girls, welcome to another day of Virtual Career Day. We are so excited to have this opportunity, that we have people out there that are willing to really help us and really willing to make this possible. I know it was devastating when we missed Career Day, but we can make lemonade out of our lemons. And so here we go, Virtual Career Day with Tim Colyer. Welcome, Tim.
Hi, thank you. How we doing, everybody? I'm not the most tech savvy, so I apologize if this looks amateur, because it is amateur. I work as an engineer at the Lake City Army Ammunition Plant in Eastern Independence. I've been out there for 12 and a half years now, and I work as a manufacturing engineer and as a project engineer. I got my degree from the University of Missouri. I graduated in 2006, so 14 years ago. And I've worked at Lake City my entire engineering career. That's a little rare. Engineers nowadays tend to move around a little bit. That's a very common just a common job path. They'll work somewhere between 2 and 5 years, and then they move to a new position. I would say probably about half of the engineering workforce is transient like that. They move from job to job, and they do a variety of things as they move from job to job. It just kind of keeps it interesting, and it's one of the perks of being an engineer. If you want to try a lot of different things, you have that ability to do that. And there's a lot of demand for that, because there's things that apply in certain industries that can apply in other industries. And so having engineers that move around like that helps translate that technology around. I have a degree in mechanical engineering, which means that I have been trained about motion and how things move. I've been trained about materials and what things are made of and how they interact with each other, and what certain materials are good for certain applications. And I have a general understanding of a lot of the other engineering disciplines. I wouldn't be an expert in any of them, but I can hold a very basic conversation with a lot of other different types of engineers. So there's electrical engineers, chemical engineers, civil engineers, and that could cover transportation and infrastructure, buildings, roadways, bridges, so yeah, mechanical engineering in general is the engineering degree that covers the biggest area, the broadest thing. So if you're not sure what you want it to be, mechanical normally is a really good choice. Sometimes people know exactly what they want, and that's great. You can just dive right into that engineering discipline, go crazy. But for me, I didn't know when I started, and so I picked mechanical, and it worked out pretty well. Now, that's my degree. My job is as a manufacturing engineer, and so what I have been doing for the last 12 and a half years is learning all of the different processes that we use at Lake City to make ammunition. And so I have some examples here. I hope that they translate well. So this, I say little guy right here, is called a 5.56 round. And the reason we call it a 5.56 round is, well, hold on. Let me back up just a second. Let's go over some anatomy real quick. So this part right up here, and I'm sorry if that's not focusing very well. This part up here, the brown and the green part, that's the projectile. That's the part that you can see, and it's inside this yellowish part here, and that's called the casing. And the bullet is inside the casing till about this depth. So this portion of the case we call the neck. And almost that entire portion of the neck inside is how far the bullet is seated in there. And then on the bottom here, you can see a tiny circle inside the bigger circle. This is called the head of the case. And that tiny circle inside there is called the primer. That primer is what the firearm uses to initiate a round. And then inside, between the bullet and the entire inside the case is the propellant or the powder. So the primer will initiate the propellant inside, and that causes it to ignite. And then as the powder burns, the gases generated are hot and they expand. And that expansion of gas propels the projectile of the bullet down the rifle of the barrel and then downrange. So this is a 5.56 round, and we call it 5.56 because the diameter of the projectile is 5.56 millimeters in diameter. And so then another projectile we make is a 7.62, and you can see, hopefully, and I'm not holding one closer, that they're the same next to each other, so one is bigger. And this guy is called a 7.62 round. And so by the same reasoning, it's 7.62 millimeters in diameter at the biggest part of the diameter of the bullet right there. And then all the things about the anatomy are similar. So the bullet, case, the primer, and then there's propellant inside. And then we make one last one, and I don't know if I'll be able to get, so this is 7.62, and then this big guy right here is called the 50 cal. So with the first two, they're in metric. They use millimeters, which is a unit of measure for length and distance. And this is 50 cal. And 50 cal is an inch. It's an inch-based system. A caliber is an inch in diameter, and a 50 cal is 0.50 calibers, 0.5 inches. So it is a half of an inch in diameter at the widest point of the projectile. And the projectile is roughly the size of my pinky. So it's way down into the case. It is a very large projectile, and it is primarily used for airplanes. Some airplanes and some helicopters use it to kind of engage each other. And then on the tops of Humvees, if you see a person riding around up there, sometimes they might have a 50 caliber mounted up there. And it's intended to engage light armored vehicles. It's not for people, it's for equipment, to disable the equipment so it can't run. So maybe the engine block or what have you. And so those are the three calibers that we make at Lake City, and we make them from almost raw materials. So the raw metal comes in these little cups that we draw out and form into the shape of the case and the bullet jackets. And we make the primers from brass strip, and we form the primer cup. We make almost all the chemicals that form the primer on the inside. We buy the propellant. We don't do anything with the propellant. That's manufactured somewhere else in the country. They ship it here. And the projectiles, we get big bars of lead, and we stretch those out into thin wires and then process them. And that's what's generally on the inside. So this outside is copper, and on the inside is lead. And we'll draw out a copper jacket into a thin, long tube with a base, and we point it out and make it at the point of the bullet. And then we shove lead down inside of that cavity that we just created, and then we close the back end of the bullet up, and then we'll load it into the cartridge. So, anyways, well, I could talk for a very long time about the projectiles, but that's not really that is why I have a job at Lake City, but that isn't really what I do at Lake City. So I will try to do my best. So I have some things on the table, and I'm going to try to flip the camera. There we go. Okay, so just kind of scan the table really quick here. That's some of the stuff that I have. Let's come over here. So as an engineer, we do a lot with math. We do a lot with science. We kind of need to be pretty good at English and reading too, but predominantly we're known for math. And one of the ways that we use math is we measure things. Okay, so you probably recognize the first thing I picked up there. This is just a steel ruler, and you can see that there's measurements on there. You have the inch, 2 inch, 3 inches. Perhaps you guys have used a ruler at school to measure the length and the width. And that's a good way of measuring things, but it isn't very accurate because you have to make sure, I'm sorry it's so dark, but you have to make sure that you've got it all lined up correctly. And so one thing that you can use that's a little more accurate is called calipers. And these calipers are digital, so it puts the number out there. Right now it's zeros because the caliper jaws are closed, but I can open the jaws like that and you saw the number change. And so that number tells me what the size I'm measuring. So if I come up here onto this bullet and I clamp down on it, you can see that we're measuring 0.5100 with a diameter bullet. And that's actually correct. When I say that this is 0.50, that's not the exact size, that's just the general size. So this particular bullet is measuring 0.510. So there, when I give that number on 5.56, 7.62, 50 cal, that is not necessarily the exact number that they measure. And that is a very important thing to understand as an engineer, is that sometimes you use numbers to generally describe something, and then sometimes you use numbers to specifically describe something. And so you will have the opportunity to know the difference. So I can use the calipers to measure something, and then I can also use something called a micrometer. And that, I don't know if I can operate it, but so this knob here will spin, and as I spin, the jaw will retract very slowly. I have to spin it a lot of times to get it to move. And that small movement creates a very precise measurement. And so if I wanted to define the size of the diameter of the bullet even further, so I could tell 3, maybe 4 decimal places. So I can go 0.510 pretty accurately. With the micrometers, I can add more decimal places. So I can go 0.5103 maybe, or 3.1 potentially. And the reason that I have these out here is that as you take measurements, some things are better to get a fast measurement. You can get a pretty fast measurement with the ruler. And some things you can get a really accurate measurement. I can get a very accurate measurement with the micrometer. And some things I need a quick measurement, but I need it to be more accurate than a ruler. And I can use the calipers. And all three can give me a measurement that is the same thing. They can all give me a measurement in inches. But sometimes I need it to be really accurate, and sometimes I need it to be really fast. And you have to know when you're dealing with measurements which attribute you need to capture. So is it something really quick, or is it something really accurate? Another thing that we are really concerned about when we make ammunition is weight. And so this is a very portable scale. We would use something much bigger at the plant, but it does work very well. So we will turn it on. Oh, no. Okay, well, we'll just use our imagination. So the display right here will work just like the calipers do. And we have a little calibration weight. And so I set that on there and I make sure that the number that the scale is reading matches the weight of this calibration weight, which is 10 grams. So I need them to match, and if they don't match, I can tell the unit to recalibrate itself to that 10 grams, and then I know that the scale is right. And then I can go and I can stick the cartridge on there, or if I just had bullets, I can put bullets in cases or whatever, and I can measure that. And the accuracy
of the round can be dependent on the weight. And there's the physics behind that, why the weight is important. And you'll get to learn that as you mature and grow in the sciences and whatnot, with the laws of physics, the Newton's third motion of law, or the second law of motion, and the laws of kinematic equations, and dictate how projectiles will function as they move downrange. So anyways, so part of the thing you have to do with engineering is using math and defining things accurately. And then another thing is to help keep people safe. So I just want to quickly kind of go over all protection, we call it PPE, personal protection equipment. And so when we make ammunition, we deal with things that can be rather dangerous. The powder and the primers, and a lot of the things that we use are what we call energetic, and that means that they can have an explosive, or they can emit energy in a dangerous way, mainly in a way that would hurt a human body. And so when we handle devices or products that are energetic, we have to wear special clothes. So one of the things that we'll wear are these shoes. They're called conductive shoes. And the soles of these shoes have tiny copper fibers interwoven in them. And they go all the way through the sole of the shoe. And the insole has the same properties. And it's kind of gross, but as your feet sweat in the shoe, your sweat lets your body come in contact with the fibers in the shoe, and you become what's called grounded. And so you can conduct electricity through the bottom of your feet to the floor. And then we have these special floors that then take that grounding and move it to a safe space. And so like in the winter, you're on the carpet and you shuffle your feet before you can build up static electricity. Well, some of the energetic material, if you were to touch the light switch at work and generate a spark of electricity, you could ignite some of the energetic material. If you're wearing these special shoes, that prevents that ability to build up static electricity. You release that energy into the floor safely. So it's very important to wear our conductive shoes so that we don't generate static electricity and put ourselves at risk for an energetic event. Another thing that we'll wear is this green coat, and it's made out of a material called Nomex. Nomex is a fire retardant, and so if we were in the energetic wing and forbid that this should actually happen, but a fire is created or an explosion of some sort where there's people can get hurt. Generally, that also will result in a fire, and this will help protect our bodies from. Step it up a second. Okay, this will protect our bodies in the event of a fire. And then, of course, we wear gloves to protect our hands. We wear safety glasses to protect our eyes. And then we also have these special earplugs, which fit exactly into our ear canal. So my earplugs, they only fit my ears. So a lot of the folks on plant have these kind of custom earplugs that are only the size of their ears. And then one last thing I'll show you is this guy over here. And so it's a full-on jumpsuit with legs that go all the way down. And when you put this on, you're basically in a blue suit that goes all the way down to your wrists and down to where your pants would normally end and up to the neck. And we affectionately call these Smurf suits. And when you wear these, it just does a better job. They're made out of the same Nomex material as the green jacket over there, but it just does a better job of protecting your legs. And you can Velcro this down to your wrists, whereas the jacket just kind of hangs there. It doesn't have that ability.
anyways, this is mainly for people that are going to work in the area or have direct contact. This is for people just hanging out, like engineers. We generally don't touch the energetic material. We just observe. We're in the area. We wear this for protection. But if they're finding off chance, we do have to be in direct contact. We put our Smurf suits, and they will do a much better job of protecting us. So, so I think that probably concludes a lot of what would go into at least some of the aspects of my job. Now, I'm led to believe that there might be some questions. Ms. Knight, I think you're still on mute, perhaps.
All right, there we go. So what kind of school did you have to do to complete? What college did you have to go to, or did you go to high school? Where did you go to be able to do your job?
Gotcha. Okay, so I went to Fort Osage High School, which is in Eastern Independence. I graduated with a high school diploma. Anymore, when you're in high school, there are engineering specific classes that you can take. When I was in high school, my high school didn't really offer very many engineering specific. There was advanced physics and calculus, and I took as many of that as I could handle. But now there's problem solving classes and there's creative classes that really help out a lot. So if your high school offers it, which I believe they will, because most high schools are getting very good at offering engineering related classes. I would take as many of those as you can. Even if you end up not being an engineer, there's just a lot of good practical experience you can get. Just thinking critically and trying to do problem solving and all that exposure. And then when I got to college, I went to the University of Missouri for 4 years. Anymore, if you're going to do engineering, it can take up to 5 years. They've just got a lot of things they have to cover in a short period of time. And then I graduated with a bachelor's of science in mechanical engineering. And then there's opportunities to go back and get masters and PhDs, and you can get your professional engineer's license at some point, which like makes you a super engineer. Lots of opportunities. And then another really cool thing about being an engineer is you can springboard into a lot of other things. You can go get your lawyer's degree and become a patent attorney. You can go get a medical degree and become a specialist in orthopedics or biological reform, medicine. You can get your MBA and start your own business. And there's just a whole lot of things that you can use that engineering degree for later on in life that you don't have to use to right now.
So I've heard that engineering is a really, like, we think it's kind of a smaller area, but there's so many things that you can do. When you were in high school or middle school or elementary school, what was your favorite subject? Was it always science? So were you on that path and you knew you were going to be on that path?
I have always found math to be easy, probably one of the easier subjects, and then I've always had a really strong interest in science. So I would agree with that. And then I was fortunate enough to be able to take higher level math earlier. So we had a program where you could take, it started in 7th grade, and you could take pre-algebra, which is kind of like you wouldn't normally take pre-algebra until 8th grade. And by doing that, that really helped kind of solidify that by the time I was in high school, I was in a place where I could have exposure to mathematics and even some physics and stuff that I wouldn't have been able to take otherwise. Now, that isn't to say that you don't do those things, that you can't be an engineer, but it does help a lot to have that kind of interest.
Very good. And what is your favorite part of your job?
Oh boy. Well, my favorite part of my job generally is showing the plant. So every now and then we'll have visitors that come in. They could be part of the military. They could be one of our suppliers. We have supply almost all of our raw materials and all things we use has a supplier off plant. They'll sometimes come visit, or maybe we want to buy a piece of equipment, or there's just all sorts of avenues where we'll have visitors that come to plant. And unfortunately, you have to have a good reason to be there. So it's not like I could open up an invitation, hey, show up and I'll give you a tour. But every now and then, maybe once a month, every other month, I'll have an opportunity to take somebody on a tour of the plant. And the plant has been there for almost 80 years now. It was started by Harry Truman. It has a lot of historical significance for the area. Almost every family in the area is affected by the plant's existence through employment at some point in those 80 years. If you have relatives that lived here, I almost guarantee almost everybody has a story of somebody who worked at Lake City. It's an important part of independence, and it's an important part of our nation's defense industry. And I love showing that off. I love showing all the old equipment that we still use today. I love showing how the buildings were constructed, and just being able to get that kind of exposure. It gives you a really good sense of pride in what we tried to do 80 years ago and what we're still doing today.
That's fabulous. And Lake City is here in Independence, right?
Yes, ma'am. If you take 23rd Street east, and it literally runs right into the plant. That Circle Drive out east of Independence, that's the front gate for the plant. And
wonderful.
It's not quite 5,000 acres, about 60 miles worth of roads. It's quite a place.
Yeah, huge. Well, Tim, thank you so much for visiting with us virtually. I know it's not the same. I know they're not in person, because I know in the past the kids get so excited when you pull out those bullets, and they just are like, oh my gosh, they don't get to see them up that close very often.
I'm a little disappointed we didn't get to do it face to face this year, but I'm glad I got to participate. I look forward to seeing everybody next year.
Perfect. Thanks again so much, and have a great day.